hope everyone got lecture 7. Any questions about the lecture? Like the past lectures? Okay. Any questions, concerns about the project? Is it coming along well?
Yeah, it's coming along really well, Professor. Our group wanted to ask when is going to be the due date for this project?
Like the last 2 classes probably. I'll be sending an email uh, like early next week.
Okay,
But you can see like what's the last date in the academic calendar. So that will be the last 2 classes.
and Professor, our group also wanted to ask you about the presentation. Can you let us know a little bit more details about how the presentation is going to look like?
Yeah, sure. Uh, Thank you so much. Actually, let me talk to that right now. So in real life, uh, to be a successful professional, and of course, since we're doing engineering, so in order to be a successful engineer, you have to be able to work in 2 settings. First setting, to work alone. You present your work alone. And in this case, you're called individual contributor. Okay? Mostly that's when you, like after like 10 or so years. Okay? And that's what you guys did in the first. So basically, you do it like very early on in your career. Um, when your managers want to see your progression, so you do solo, and after you become like a guru. Okay? But in between, say for a duration of 10, 12, 13 years or so, you'll be working with a group. And you will be coordinating a presentation within a group. So that's what I want you to learn. So all of you, like the 3 or 4 of you, like depends on how many in your group, you are going to collaborate to create slides. Okay? And the trick, all the slides have to appear to be coming from one person because you're one team, right? You know what I'm saying? So the flow has to be continuous. That's what I want you guys to work on. And I'll leave it up to you. I'll give you like the exact details, how many minutes for each team, blah, blah, blah. But I would want like, the first person will say the introduction for it. The second person will say the background. The third person will talk about the security aspect. The fourth person will talk, I don't think I have more than 4 or 5 people in the group, but you get the point. You get the gist of it. One person will talk to the opnet. Probably the first person or the last person was like, oh, John did this piece. Mary did that piece. Anne wrote this thing. Smith did the research. You have to show me each one's contribution. Like one of you will just go over each one's contribution. So probably the team leader will set the presentation. Like give an overview. Again, it's any way you guys want to do it. The reason I don't want to give like exact details how you present, because I want you to learn how to talk to each other. Because it's not gonna be easy. See, when you go work in the industry, you as an engineer, you're going to interact with 2 main things or aspects. First thing, you're gonna interact with machines. Okay, servers, computers, whatever. The second aspect of interacting will be interacting with your peers, with people. Trust me, interacting with people is much, much more challenging than interacting with computers. Okay? So many times I see very good engineers, super good, but they don't know how to work in teams. Trust me, they move nowhere. You know, they move nowhere. I've seen engineers, they're so good, don't get me wrong. Like, technically, they're so good, but they're not, they don't know how to interact with others. They spend 20 years in the same job title, almost the same salary. You know, it's just very sad. So I'm just trying to make you, like, give you a little training, very teeny tiny training, okay? Fair enough, guys?
Yes.
Yeah. So I'll tell you like how many minutes. That's why I asked you last time to send me the team members, so I know each, like, how many teams I have. So I'm thinking probably each team will be like 10 minutes. But let me send that officially after I do the calculation. Yeah, so you're gonna have a presentation, slides, and then send me the report. Okay, the written report. That's all. Just do this and you get the grade.
Professor?
Okay. Yeah.
I'm sorry, quick question. So our team, basically, we are all of us working together. We basically meet once in a week and work like 3-4 hours on the project.
Right.
So because we want to all of us understand how it's working. So when we're gonna do the presentation, since each team member basically was involved in all the steps in the project, I mean, how can we separate it?
Good. That's a very good question. You know why? Because that's exactly happened in the industry. You have 5 people, probably 4 really involved. 1 is the team leader. So that's a very typical scenario. So what you just said at the beginning, that you give credit to everyone, that everyone is involved, 3 hours, that's the same thing you should say at the beginning of the presentation. Hi, Professor. Hi, everyone. My name is Andre. And all the 4 members or the 5 members of the team, they work on the OpNet. All of them, they did their research. Yeah, that you just say what happened. But for the presentation, you use your engineering methodologies, and okay, so the presentation, like 4 pieces for anything. Overall introduction, background, design, and OpNet, for example. And you talk amongst each other. So who's comfortable in presenting what? You see?
Thank you.
You're welcome. Yeah. But no, thanks to you. I mean, you open up good question, because this is exactly what happened. But you have to show the whole world that you're one team. You know, you're gonna gain a lot of respect. You know, so like, you know, the flow, like the handoff. Like, you finish slide number 3, and now I'm gonna hand the presentation to my colleague, you know, Peter or John or whoever. You know, things will go smooth. Everyone will be happy. Okay. More questions? Okay. So they will be the last 2 dates of the semester. I'll give you the exact dates. I'll look at the academic calendar, but you can go look at them right now, and you know. And I'll let every team know when they can present. Okay. Okay, so if you don't have any questions, let's proceed. So we've been talking about layer 2. So by the way, just to satisfy the curriculum, the syllabus of the course, we're going to talk about the TCP layer next. Okay, and see if we can pick up like 1 or 2 advanced topics. So let's see what's going on here. So we talked about layer 2 for quite some time. And we said layer 2 deals mainly with directly physically connected nodes. And the whole main aspect of layer 2 is to do MAC, medium access control. You have the medium, you have 20 people inside the classroom, you have a single Wi-Fi. Each person out of the 20 has their own device. Who can access the medium first? Who can access the second? Who can access who can be the 20th? Layer 2 coordinates and arranges for this system to eliminate or reduce conflict. Why am I saying conflict? Because according to the laws of physics, two signals with the same wavelength or same frequency at the same time they'll collide. Just put two people in the room, let them talk at the same time with the same voice trend, and tell me if you understood what they said or not. Okay? So the best is to make only one person talk, then the second person, then the third person. Same thing happens with the devices. So the layer 2 or layer 2s collectively, they coordinate the process. So from the big from the big picture perspective, there are three types of algorithms or families. First one is sharing, medium sharing, and we talk about TDMA and SDMA. And so surprisingly enough, we talked about CDMA. That pretty much violated, not violated, but because I've been saying two nodes at the same time cannot transmit the same frequency, correct? At the same time. On the same frequency at the same time. But comes to CDMA, it's like, wow, there's a nice workaround. So if the two signals are orthogonal, and we talked about the coding, it's like, wow, if this happens, I can transmit as many signals as long as they are orthogonal. And literally no interference will take place. So why I keep telling you guys that no two devices can transmit at the same time at the same frequency? Because this is the truth. So when I come and tell you about the CDMA, you will have some appreciation to what's going on. You know? Because that's not the norm. And as I mentioned, 2G, some 2G uses CDMA and the majority of 3G uses CDMA. And of course, if you've been reading, following the telecommunication news, all the telecommunication carriers, I believe, will sunset the 3G support. So basically, the software in the cellular tower for the 3G will be decommissioned. What does that mean? So if you have an older handset that only talks 3G, it will be rendered useless. And I was reading this article a couple of days ago, and they were talking about the sector of the population, especially older folks and those who live under the poverty line. They most likely will not be able to afford newer phones, and there will be some issues that they cannot even call 911. At least that's what the article was talking about. Okay? So just remember that each technological advancement, or even just technological aspect, it has a human face. Okay? It's either going to make some people happy, some people sad. Just be mindful of that. As an engineer. Okay? Never separate the human impact from your engineering work. Okay? That's how you keep your job or mission meaningful. So we talked about CDMA, and we gave very nice example. Did you guys go over that example alone?
Yes, Professor.
Okay. So the example is like, again, 1,000 or probably 10,000 times oversimplified, just to show you the point, but it does not really relate to the actual CDMA. The CDMA is very complex, but this is a very nice way to make you guys understand what's going on. Because the only way, or the most efficient way to make someone understand something is to make him visualize it. And I believe that's what I did here. With this and this. You guys can hear me?
Now we can hear you.
Okay. Okay, I guess I've been talking on mute for how long I've been gone?
Like 30 seconds maybe.
Okay, thank you. So the second family of Mac Media Access Control is taking turns, and I don't think it's really a very efficient technique, and I'll show you why now. Just want to recap something about the partitioning. If you look at the 5G, you're going to find it a mix of EDMA, FDMA, and CDMA. So it just puts everything together. But if you understand the FDMA, TDMA, and CDMA, you will have less hard time understanding the 5G. It's FDMA. It's called SDMA. So taking turns, the most famous one is, so basically taking turns, it has some characteristics. That's the second family. You have a central authority that commands each node to transmit. Like basically, this single authority will tell node 28, oh, now it's your time to transmit. Good, stop. Now, node number 41, it's your time to transmit. So basically, it just keeps rotating based on a pre-configured sequence of nodes, so to allow nodes to transmit. So the most famous one is polling. Have you guys gotten the chance to look at these or not? These slides?
Sorry, Professor. I think we actually went over these slides already.
No, I know. I even have like here.
Oh, okay. Sorry, I thought you were.
I know. No, I know very well. But so here's my thing. I like every class to spend like 10 minutes recapping. So for those who haven't gotten the chance to look at the slides.
Yeah, it's actually a good thing because it connects the subject better. Yeah, like when you recap. But No, I said you connect like the two lectures better when you recap. So that's it's a good thing.
Thank you. Yeah, I mean, I know not everyone can get the chance to study, so when I like to recap, so at least you heard it twice. One was like full length of the lecture, and the next time is like super fast.
Yeah, I'm sorry, I didn't
I
mean
mean,
to be
my goal is
disrespectful.
no, that's good. It's good, but yeah, I'm aware of that. I mean, just my goal is to make sure that no one is left behind. So yeah, polling. You have the polling overhead, the latency, but the main problem, as we talked last time, is a single point of failure. Okay. And as I mentioned last time to you guys also, it's a big no-no. Having a single point of failure, it's a no-no. Then we talked about token passing, and we said it's a piece of software, and again, it's a single point of failure. And we brainstormed together for like 8 or 10 minutes last time how a malicious hacker can exploit the token passing. Okay, so basically, token pass is like a piece of software application. It has a predetermined sequence, so a hacker can just drop the file, corrupt it, not transmit it, alter some information or an instruction inside it. Again, there's so many things, bad things can happen. And that's one of the reasons why this family of algorithm did not really take place. So any questions so far? Okay. So now we're going to talk about the random access protocol. Just for you to have some appreciation. So first of all, most likely, on the final will be the random access protocol. From this slide 35 to towards the end. I haven't put the exam yet, but most likely, that's what I focus on. Okay. That doesn't mean that like the previous stuff are not valid. I could get it from anywhere, but the probability or the possibility that I get it from 35 to forward is much, much higher. So, if you look at any device you possess, laptop, cell phone, it doesn't really matter what it is. As long as the device is Wi-Fi capable, so that means it uses this mechanism, the random access. Most of the random access protocols, they're called 802.11. Okay. This is the de facto Wi-Fi. So that's what it's called. So 802.11. And you find like letters A, B, I guess F, G. So when you go buy a laptop or you buy a Wi-Fi router, you're gonna find what are the supported. Okay, they're all 802.11, and this is the random. The main difference between a version and another, mainly two things. First thing is the speed, because every time you get smarter algorithms, you get more sophisticated hardware. So you go from A to B, B to F, or F to G, or there's B and there's like so many letters. You guys can go look them up. So you go. The more recent ones are much faster. Also, they add patches for security. So they add intelligent algorithms that make security enhanced. But all of them are based on the random, okay? 100%. So let's talk about the random. So one big aspect in the random, there's no priority in the action. Priority meaning prior coordination between the nodes. So each node can act on its own to transmit data, and the goal is to transmit at the full channel data rate. Okay? So since it's random, you cannot leave 100% random. So scientists or engineers said, well, if you want to follow the random protocol, at least have 2 checkpoints to make it less random or to make the randomness more controlled. So the first aspect of the random, of the chicken controlling the randomness, is how to detect collisions. So they said, well, yes, you can have your randomness, but offer me a method on how to detect collisions and how to recover from those collisions. So engineers said, or scientists said, well, if you can offer me those 2 features on top of the random, I will be able to survive this randomness. Okay? So the first viable random protocol is called Aloha. It came out in the 1970s in Hawaii. And I believe it was introduced as a research paper or publication, something like that. So that was a breakthrough because everyone back then thought it was like, oh, let's have polling, let's have channel partitioning. Because even the word random, it does not really go hand to hand with engineering aspects, right? Because engineers, when they hear the word random, is like, how can I get rid of randomness? You know? So that was a kind of weird concept. But thanks to the open-minded engineers and scientists, that before they say no to something, they look deeper and deeper into it, so they can make educated judgment. So what happens here? Aloha, they said before, if you have a packet to transmit, just transmit it. No worries about any other person. And they achieved maximum efficiency of 18%. So every 100 packets you as a user transmit, 18 will succeed. Or if you put it into another perspective, every 100 transmissions into the medium, 18 will reach the that collision. So 18, that's the best case scenario. So let me talk to you about a little mathematical piece. So in a Wi-Fi setting, what is the variable that could impact the efficiency?
The medium.
There's not really a variable. The medium is constant. But thank you for answering.
Maybe like when you send the data, maybe like when you send the
That's not your primary variable.
The bandwidth?
Not really. The bandwidth, you're given a fixed spectrum to transmit on. So that's a fixed constant on the macro level. Like think in a classroom. What could impact the efficiency of the Wi-Fi?
Or the amount of people who are using it?
Thank you. So number of users that need to access the medium. That's your primary variable, right?
Yeah.
The more people you have, the less efficiency you will get. So here probably they were talking about 2 users. So basically, let me draw this for you guys. Share this screen. So it goes something like this. The maximum efficiency you get. So this is efficiency. And this is number of users. And number of users, okay? So you get something like that. You start from 18 and you go all the way to this is 18. So the best probably like if you have two users at the median, you will get 18%. And the more you add people, you're gonna keep going down to a point called saturation point. When the medium is fully saturated, that means collision happens 100% of the time, and that's what you get, like zero efficiency. Is this clear to everyone?
Yes.
Okay. Then that was good breakthrough actually, because people when they hear random, probably they thought about zero efficiency, but 18 wasn't bad for that mechanism. Then later on, someone said, let's make something little advancement on Aloha called slotted Aloha. So what they did here, they said, okay, so let's divide the time into slots. Like if it's 1 second, like 10 slots. It's still random, but everyone wants to transmit. They only transmit at the beginning of the slot. And if you have something mid-slot, no, just wait and only transmit at the beginning of the slot. This is a very small advancement, or like minor modification, I would call it. But the result, look at the screen. The efficiency doubled. Is 36%. You guys see that? 36%. Here's like a lesson I want to teach you. So most of the PhD dissertations and the R&D work around this area. What a minor improvement that you can make in the algorithm, in the hardware, in the system, and the efficiency will increase dramatically. Imagine if the slotted Aloha increased the efficiency from 18 to 19 or 20. You think anyone would have cared? No. But it was very intriguing. To find that with a simple modification, literally it's like a few lines of code inside the algorithm. It's just basically you're commanding each node, hey, at the beginning of the communication session, sync up, your clocks, get the time slots, and you're only allowed to transmit at the beginning of the time slot. That's all. When the time slot clock ticks, you transmit if you have a packet. If it's not ticking, you don't send anything. So minor improvement doubled up the efficiency. That's what we're looking for, actually. And that, just a concept for your own knowledge. You find like when phone carriers went from 3G to 4G, before actually upgrading the hardware, you could find like 4G trial, or 4G evolution or packet evolution, whatever the name. And the same thing happened with some carriers for the 5G. They did not really have 5G hardware installed, but they start propagating to the cell phones 5G evolution or 5G plus or something like that. How? When they were asked, the telephone carriers, they responded that, yes, we are not there yet with the 5G. That was like 4 or 5 years ago. But we pushed software, more intelligent algorithms that make phones are super fast. And actually, this was something that you could try. Like, you have the same hardware, and people use 4G, and others have the 5G evolution. It's the same hardware, but the 5G evolution, they use modernized software, and the speed was like dramatically different. So before actually they put the actual 5G equipment, okay? But bottom line, software can make things much, much better if it's done right in an intelligent way. Okay? So, as you see, guys, here, this is Aloha. Anyone transmits whenever they want. And then they got slotted Aloha. Here are slots. Either you transmit at the beginning of the slot or you don't transmit. So what it did, it narrowed the window of collision. Because the window of collision here between any two nodes was potentially 100%. Because both of them, they can transmit at any time. Multiply that by the 6 nodes. So continuously you had collision possibility. But here, you kind of narrowed down the collision window. But again, that was good for...
Professor?
Yes.
So basically, like, because they start at the same time, that's mean like each one of them is gonna be random. So it's more randomized because they start at the same time, so less collision, right? But if they start at random, they have more chance to collide.
Yes.
Okay.
But let me put things into perspective. The 36% is not good enough for today. That means if you have 10 people inside a classroom, about 3 or 4 people will have their internet connection good, and 6 or 7 people are like totally out. Not totally, but most of the time they're out. So it's not acceptable for today. But I'm just showing you how things evolved from Aloha all the way up to fully 802.11. But 802.11 is based on Aloha, by the way. Okay, let's proceed. So, as I mentioned, and if anyone can remember, 10 minutes ago we said scientists or an engineer said, well, if you want really to do random, we don't really like it, but you can do random. Given 2 conditions. Can anyone remember those 2 conditions?
Predict
Oh.
collision
And recover from them.
And recover. Thank you so much, guys. Exactly. So if you want to go ahead and do random, that's okay. No, it's no big deal. But you have to be able to do 2 things. Detect collision and recover from collision as fast as possible. So that's why carrier sets multiple access CSMA came to play. So CSMA, what does it do? So in pure Aloha, or in the crude Aloha, plain Aloha, what I call it, if you have a packet, just transmit it. just spit it into the medium without caring about anything else in the whole universe. CCMA introduced one rule. CCMA said, look, well, before you transmit, turn on the antenna and check if someone else is transmitting. Since again, we've been saying that layer 2 can hear each other because it's about physically directly connected nodes. So if node A transmits something to the Wi-Fi router, node B definitely will hear it because it's the same classroom, same range, same coverage area, correct?
Yeah.
So before you transmit anything, turn on your antenna and check if someone else is transmitting. If someone else is transmitting, hold off from transmitting for a period of few milliseconds till the medium is clear. Go back before you transmit. Listen again. How do you like this, guys? What are your thoughts? It's a very simple act, but it's very brilliant, right? It's used the same hardware, which is antenna, and added a little software just to force the antenna to work a little early. So CSMA, what it did again, before you transmit into the medium, just listen. See if someone else is talking or not. Like the same way if we're in the physical classroom. Before you talk, you just want to make sure no one else is talking, right? Otherwise, it's going to be rude. So same thing happens here. The network just checks and sees if someone else is transmitting something. If no one is transmitting, then everyone is in the clear. This dramatically reduced collision. Any shortcoming from this algorithm or any potentially not so good scenario could happen at CSMA.
If it's a long transmission.
I'm sorry?
It's a long transmission.
Why long transmission?
It would take longer for the next signal to send.
It's okay. It's okay. And by the way, in 802.11, no one really transmits on continuous basis. And we'll see that in the last couple slides. Each one transmits only one packet. But thank you so much for stepping in and answering, attempting to answer. So, can anyone else tell me what could go wrong in this scenario?
If you have a lot of users, then it would always be busy.
But that's the nature of it. I agree with you, but that's the nature of it. If you have so many users, again, sorry, no can do anything because you never promised to accommodate 2,000 people in a single building, on a single Wi-Fi router. You always give the limitation. So this is like a hard limitation you cannot really break. But that's a good way of thinking.
What if
What if you, for example, you can transmit it? For example, somebody transmitting something, and you didn't recognize that they transmitting, and you start to transmitting also.
That's a good way of thinking, but no, you will really, because everyone is transmitting using the same frequency. If anyone is transmitting, you will know it right away. So let me tell you what could go wrong here. Nodes A and B at the same exact time, they sense the medium. They found it to be clear. And both at the same time, unknowingly, they transmit. You see the vulnerability here?
Yes.
So they said CSMA is very good, but this is a weakness that two nodes will sense the medium simultaneously, come to transmit, successfully transmit, couple microseconds after, boom, a collision happens. So they said, okay, so let's see what we can do here. So they introduced something called collision detection. So now it's, instead of CSMA, now it's CSMA/CD, carrier sense multiple access / collision detection. And that's the Ethernet, guys. The Ethernet that everyone is using. You know the Ethernet cable or Wi-Fi? That's the same thing. See how we went from like very rudimentary technology all the way up to what we're using today. So CSMA, you listen to the medium via your antenna before you transmit. Collision detection, just like in CCMA, once you hear the medium is clean, you transmit and you shut off your antenna. But the collision detection module, the CD module, is like for the CCMA part, you listen to the medium is clean, clear, transmit. Collision detection forces the antenna to stay on. So the antenna now is staying on because the antenna is very sensitive and it can distinguish between an actual transmitted signal and a collision. So it will know, the antenna will know right there and then if a collision happens. And that's how it can recover from collisions so early. Because it's not going to wait for a missed acknowledgement from the receiver or a timeout just to know that the packet was lost. No. It knows in real time, right there and then, if a packet is lost, if a packet collides. Everyone understands this?
Yes.
So we'll say it one more time. So people who have not been following 100%, now please follow. So CSMA, before you transmit something into the medium, you turn on your antenna, you listen to the medium. If the medium is clear, you transmit. But the problem is, two nodes unknowingly could be sensing the medium at the same exact time. They find it clear, boom, send, collision happens. To detect the collision as fast as possible, because we are talking milliseconds. Guys, look when you talk to your friend or your family member in Europe, in Canada, in California, some far away. The call is crystal clear. How and why? Because engineers take care of these protocols and try to save every microsecond. See, it's 2,000 miles from here probably to the destination if you're calling someone. If I'm going to miss a couple milliseconds here, a couple milliseconds in the LAN, a few milliseconds in the core, a few milliseconds in the cellular tower, that will add up like a couple seconds. Then the voice will not be clear. But that's not the case. We get very clear voice. How? By taking care of these little aspects, one at a time. I'm just trying to show you how significant is saving every microsecond, in the telecommunication link. So the CD piece here is after I transmit, I keep my antenna on and I make sure that the signal arrives to the Wi-Fi without collision. And if it collides, I know right away and I prepare another copy and attempt to transmit instead of just waiting for things to happen for me and some other external node or entity telling me, oh, this packet is lost. No, I know it for myself. So 802.11, there are like so many flavors algorithms, but I just chose one called DCF, Distributed Coordination Function. But again, there's so many of them. And basically, if you understand one, you understand all of them, just minor variation. So just focus on the keywords, IEEE 802.11. So basically, focus please here very well. You see my screen, right? So you guys can hear me, right?
Yeah, we can see it.
Okay. So you have three nodes, A, B, and C. A and C, they try to communicate with B. So what happens? A listens to the medium, finds the medium clean and clear. Clear like no one is transmitting. Clean like no collision. Because there could be other two nodes colliding, like transmitted and collided. So A listens to the medium, finds it clear and clean, and sends an RTS. RTS, that's the request to send. So since the, and this layer 2 protocol, so since this is the layer 2 protocol, everyone in the coverage area will hear it. So B will receive it, will open the RTS, will parse the bits, and will find that the RTS is distant to B. So A is asking B, can I transmit? At the same time, C, it will receive the RTS, and once it opens the RTS, will find it's distant to someone else, distant to node B. Then it was like, oh, it's not distant to me, but in the RTS, there is a value that A is anticipating how long this transaction will take to transmit data, which is a packet. So C was like, oh, in the RTS, it says this transaction between A and B will take 10 milliseconds in a field called NAV, Network Allocation Vector. So NC will take the 10 milliseconds and will refrain from transmitting anything during that period so it not interfere between A and B communication. Of course, assuming C is a good behaving node. If C is a hacker, it will just disregard the nav and will transmit things, cause collision. So B will find the RTS distant to it, and it will review its own protocol. It's like, oh, I can talk back to A. I can. There's no rule preventing me from talking to A. I'm not talking to anyone else. I'm not waiting for anything else. So I am in a state that's ready to talk to A. So B will send a CTS, clear to send. Then A, once it receives the clear to send, it will send the data normally to one packet. Once B receives the data, we'll run the error detection checks, like parity check or something like that, or CRC, whatever that is. Then, oh, I received it good. Then B will send an acknowledgement, signaling the close of the four-way handshake. So four-way, RTS, CTS, data acknowledgement. And that signals to everyone in the whole coverage area, like think of a classroom, oh, this transaction is finished, and the median's up for grabs. Questions? Okay.
What did you say RTS again? Like as beginning of the transmission? Clean and clear?
Yeah, so RTS, request to send. CTS, clear to send. Okay?
Okay, thank you.
You're welcome. One thing I did not really discuss, so you have the diff and the SIF. Okay, they're described here. So diff, that's the waiting period. You guys remember the guard between, like when we talked about TDMA, the guard between the two time slots?
Yeah.
So this is the guard, basically. So the diffs is the guard between each transaction, and the sifs, like once two nodes talking to each other, that's between the two nodes, the two packets, the packets between the two nodes. But if a node tries to talk to one, like before the four-way handshake, is like the diff. Cis is like very small because they're already expecting each other, A and B. So cis is very small. This is kind of longer. It just gives like a breather to the whole network. Okay, no one transmits from the diffs, so they can, coordinate internally and see what they can do. And just to show you how important the diffs and the cis, so the cis and the diffs are good or bad for the equalization. No, good. It's not good. You're not transmitting anything on the cis and the diff. It's just a period of silence.
Yeah, but it's
not
good,
good.
because there is a reason why they're using them.
Good, but you as an end user, does it really contribute?
Yeah,
it does not contribute to you at all. You don't really care. You're watching a movie. You want every single packet to be loaded with visual description to enhance your movie watching experience. So the cis and the diffs, when I was doing the PhD, guys, I believe the cis was like 50 milliseconds in the older models, and the newer models went all the way 10 milliseconds. So you save 40 milliseconds, and you can use it in transmission. And believe it or not, this is one of the main aspects in the different speeds. You find like the newer Wi-Fi version like super fast, and the older one like slow. A major contributing factor is the size of the cis and the diffs. So now you understand how the cis and the diffs are very important? Yes? No? Maybe?
Yes.
It is extremely important. That makes like huge difference in the speed. And of course, like the newer algorithms depend on like fancier hardware that can distinguish like very accurate and precise, and it's like internal ticking and clocks. It can differentiate between 10 milliseconds and it will not interfere. So that's a major contributing factor for the speed difference or variation between older and newer models. These little unused silent periods. Okay, so let's continue here. So now after the act, now the medium is up to grab. So nodes A and C, they wait for this period. Then they listen to the medium because they want to transmit. And the perfect error happened, which is the two nodes listen to the medium, they find it clear and clean simultaneously, and they transmit at the same time. What happens when they transmit at the same time?
Collisions.
I'm sorry?
Collisions.
Collision, thank you. So nodes A and C want to transmit to B, they wait, and they listen to the medium. At the same time, clean, clear, good, transmit, boom, collision happens. So once the collision happens, each node has an internal timer, like random generator. So node C played its random generator and told it, okay, don't transmit for 2 milliseconds, and after 2 milliseconds, try again. And the random generator in node A, it told her, like, don't transmit for 6 milliseconds. And after 6 milliseconds, try to transmit again. So basically, this is like a sleep mode, the 6 millisecond and the 2 millisecond. So who would wake up first from the sleep mode to try to transmit, C or B?
The second one you said, 1 millisecond.
I'm sorry, C or B?
The one you said wait for 1 millisecond. Or the 2 millisecond.
Yeah, so it's the C, node C. Yes. So node C will wake up first. it will sense the medium, will find it clear, and it will send RTS, then CTS data acknowledgement. So once the node A wakes up after 6 milliseconds, it will find already communication happening between node B and C, then it will refrain from transmitting for a certain period of time. Okay, and that's how our Wi-Fi works too. Questions?
I'm sorry, can you re-explain that part on the right side again of the picture?
Sure. So after the acknowledgement here, that signaled to everyone in the medium that the channel is up for grabs. So node A and C, they want to transmit to node B. So node A and B send nodes A and C, they sense the medium, they find it clean and clear. They both simultaneously transmit, and their packets collide. Since they have a CD, collision detection module, CD, they had their antennas on. So they realized that their packets collided. So you have this and this. So in the disk here, after they collided, each node has an internal random backup off generator. So basically you run the algorithm, it's just a little routine, software routine. And you get a duration, a period. For this period, this node has to refrain from transmitting anything. Like basically it enters like sleep mode. So the C played its internal random generator, it gave her like 2 milliseconds. So it will sleep for 2 milliseconds. Then after it wakes up from the 2 milliseconds, it will attempt transmission again. Node A did the same thing, played its random generator, it gave her 6 milliseconds, that means it has to sleep for 6 milliseconds, and when it wakes up, it will attempt to transmit again. So who would wake up first and transmit first, A or C? C, because only slept for 2 milliseconds. So C woke up after 2 milliseconds, found the whole medium is clean and clear, because node A that wanted to transmit is sleeping now, and already started engaging node B in transmission, so RTS, CTS, etc. By the time node A woke up after 6 milliseconds, it had what? A communication going on between nodes C and B, so it refrained from transmitting anything. That's how contention gets resolved. Good?
Yes, thank you.
You're welcome. And I'll try to go again. Please read it, and I'll try to go again over it at the beginning of next class. Okay, but please don't depend on that. I want you to read, understand, and if you have questions for next time, that will be great. Any questions in general?
No.
Okay. Okay, guys. So I'll go over it again next class before we start the new chapter. But please take a look at it and see what's going on. Okay?
All right, thank you.
Professor,
You're welcome. Yes.
can I ask the question about the project?
Sure.
Remember when you you asking us to basically gather a simulation results showing delay and package loss versus speed, direction, and altitude.
Yeah.
So each drone is gonna have three different variables. It basically has different altitude and speed and then direction. When we gather information, it's mainly for each. It's gonna be like three different graphs for each of them, or we just have each drone set up like for example, drone one is gonna have like a lower altitude, lower speed, and like a closest direction, and we just compare them.
Yeah, that's a good question. So let me give you a general answer and a specific answer. The general answer: you are the creator of the presentation, right? And the report or the material that you're gonna present.
Mhm.
So present something that it makes sense to you, and it makes sense, and it makes you comfortable how to describe it. You know?
Yeah, understood. Okay.
Okay, but that's the general advice for any presentation.
Mhm.
But I'll give you specific advice. Get as much information as possible in the report, but for the presentation, you don't have to fill it with graphs. Probably like 1 or 2 graphs is good enough to show me that, you know, you did your work, blah, blah, blah. Fair enough?
Yes, thank you.
You're most welcome. And again, that will be conversation between you and your friends and, you know, your team members. Oh, we do this, we do that. That's what I want you guys. I want you to interact, to agree to disagree. Of course, in a very respectful manner, of course. And that's what's gonna make you grow as an engineer. Trust me, engineers are not only technical. Okay, engineers, you know, like technical, that's one aspect. But interacting with your team members, that's the most important aspect. Okay? So that's a good opportunity for you guys to discuss and see what's going on. You're most welcome. Any other questions? Okay, I'll conclude the class, and next time we'll start with the TCP. Okay? Take care, everyone.
Thank you.
Bye.